All right, so this is our final presentation for Project 2. We are Team 25, aka the Fire Being Rubber Duckies. My name is Hasan Habib.
I'm David Tith.
My name is Fausto Patino.
And I'm Fernando Ortiz.
All right, so to start out with, we got the problem definition for the project, which was to analyze bolted joints in a machine part using finite element analysis simulations to compare the performance of 3 different size bolts, which are shown in Figure 1. Different plate materials were tested, which in this case was aluminum and copper, along with different bolt sizes and loading conditions. The loading conditions had a tensile load applied to the top surface of the top plate, a shear force applied to the side surface of the top plate, and a pretension applied to the bolt. There was one boundary condition, which was a fixed support on the bottom face of the bottom plate. With the simulations, we focused on the resulting deformation, von Mises stress, and factor of safety. Overall, we are looking for a system that has the lowest stress on the top plate based on a combined loading condition, which has the tensile load, shear, and bolt pretension. Next, we will take a look at the technical content.
Here we have a direct comparison of the two materials, copper and aluminum, with the 3 bolt sizes. Both graphs display the full system's combined loading of shear and tensile forces along with each bolt's respective pretension. The first graph on the left compares the equivalent von Mises stresses. The M8 bolt shows similar values between the two materials, with aluminum being the slightly larger with an almost 3% difference. The M12, however, has a much lower stress overall compared to the other 2 bolt sizes, with aluminum having the smallest stress value with a 17% difference to copper. The M16 has the highest stress value, with the 2 materials being very similar in stress values, with aluminum being barely larger by about 1%. Next, the graph on the right compares the factor of safety. The M8 once again produces similar results between the 2 materials, with copper being only about 3% better. The M12 bolt has the highest factor of safety, but aluminum once again surpasses copper by more than 17%. The M16 bolt has a worse factor of safety, with copper only being better by about 1.5%. Next, we'll look at some simulation pictures. We have a screenshot for the simulation for copper. The top 2 display the full system, and the bottom 2 show only the top plate. On the left is the von Mises stresses, and on the right is the safety factor. The next one is the same setup as the previous slide, but for the aluminum material. All of the simulations look very similar to the 4 screenshots, so it's not necessary or efficient to display every single simulation case. Next, we have the simulation test table. This is a full data sheet with every combination of bolt size, plate material, and forces for the full system, bolt, and top plate. Next, we'll talk about the conclusion.
Based on the simulation results, the team concluded that the M12 bolt was the most optimal bolt of the 3. Based on the data seen from the previous slides, in both the copper and aluminum trials, the M12 bolt had the highest factor of safety, which, as commonly known, is preferable. The M12 bolt also had the lowest von Mises stress, which is also a preferable case, as this means it did not come close to the yield stress. Between the copper and aluminum materials, the group determined that the material that garnered the best results was the aluminum alloy. When considering the graphs in the previous slides, in both the von Mises and factor of safety results, the aluminum outperformed the copper. It was also concluded that the mesh size when running the simulations is very important and is key to obtaining the best results. When using a higher mesh size, the data will be more accurate. However, too high of a mesh size can be computationally expensive, while too low can lead to inaccurate results. Finally, we'll look at the reflection.
Project 2 has taught students on using ANSYS Workbench. It taught the basics of using features and setting up conditions with our SOLIDWORKS assembly. Understanding the boundary and loading conditions are important for students, as these things must be considered when designing a part in the engineering world. Understanding where forces are distributed on a structure is important, as applying forces on the wrong portion of the part may result in inaccurate data. Overall, this project was a good introduction to using ANSYS and getting familiar with the process of running simulations, and also troubleshooting when any issues have arisen with team members. This is Team 25, the Fire Breathing Rubber Duckies. I am Fernando Ortiz, and that is our project.